It's a really great pleasure for me to be here in Zagreb, and it's one of the greatest honor of my professional life to be invited to give the Nonveiller Lecture, because I remember very well when Professor Brandl, he was the first Nonveiller Lecture, was very excited to go to Zagreb to give the first lecture in the series. And when I have to look to all those who were invited to deliver this lecture, I'm even more honored to be now number 18 in the row of all these giants of geotechnical engineering. Yeah? And so once again, thank you very much, Father Jeppe, for inviting me to give this presentation. So as already Sonja has introduced myself and also the title of my work, you can see here on the first slide, Soil Compaction and Compaction Control, State-of-the-Art Innovation and Developments. It was the wish of the Croatian Geotechnical Society to talk about this topic. Yeah? And it definitely makes sense because I have been working in this field for almost 30 years now. And when I say almost 30 years, I started on 1st of October 1992. So it's just a couple of days ago that Professor Brandl invited me to start with a working group in soil dynamics. Yeah? And so I think it is a good reason to talk about this, and I'm very happy that it was the wish, and thanks a lot to Igor for proposing and for inviting me, because I was already invited almost 3 years ago, but then the pandemic came in between, and so everything had to be postponed. But I'm so happy that I'm here today, and now finally it is possible to deliver this presentation. Some words about Professor Nonveiller. So you know definitely more than me about Professor Nonveiller, but he was always a giant in geotechnics for me, because Professor Brandl told a lot about him. So he must have been a real impressive character. And here are just some impressions about him, because you know there is a close connection to Vienna. He studied in Vienna, and he was most obviously the first Croatian student of Terzaghi, because he attended 2 lectures in the first year when Terzaghi was appointed professor at the university. So here in the top, for instance, you can see the registration books, or index, as you say here, or here the application for the first state examination, and 2 pages out of his lecture notes. And thanks to Professor Virklian, who brought them to Vienna almost 3 years ago, it was possible to have a look inside, and they're really impressive. And these are 2 pages where he just had made some notes about the odometer, which was developed at this time by Karl von Terzaghi. And this odometer, for instance, is still in use. So already Terzaghi had it in his hands, and we still use it today. And what is also impressive, here is an excerpt of the letter from Professor Nonveiller to Professor Veric, and it is in German stenography. So he was always short writing, and this was interesting. This was a letter from 1998, and he still did some notes in German. Yeah? So it was most obvious his second language after Croatian. And if you have a look to that, what's Professor Nonveiller and Professor Terzaghi left behind, just an impression out of the year of 1919. Here beneath the president from this time, Igor Sokolic, visiting us in Vienna. We had the Austrian Geotechnical Conference with the Vienna Terzaghi lecture together with Professor Brandl. And then some weeks later we saw again in Omish, and with the 17th Nonveiller lecture of Professor Bala from Italy, and the amazing presentation from Professor Virklian. It was really wonderful work. Even you presented that time about Terzaghi and the Croatian cast. And we talked about Terzaghi in the laboratory a lot before and even after. And I told Professor Virklian, it is just a couple of weeks remaining to visit the old laboratory, because we moved the old laboratory. And so a Croatian again was the last one seeing our old laboratory, which was founded by Terzaghi. And this was his visit in Vienna in May 2019. And this, for instance, is the first triaxial apparatus which was developed. But no worries, we could save exactly this room. And during the next international conference, which will take place in Vienna, so it's a great honor for us that we have it in Vienna in 2026, we will officially open the archive of Terzaghi. So everyone who is interested can see it then again. Yeah? But even you were the last who could see it in person before we moved the laboratory. Yeah, coming to my topic now. Maybe a motivation why to talk about soil compaction. Here in the top you see two major projects, one Perugia Dam designed by Nonveiller on the left-hand side, and the Liesertal embankment, a project in Austria designed by my predecessor, Professor Brandl. And one aspect that was most important for both of those projects, it were the settlements, the self-settlements, the so-called compression of the dam itself. And it is mainly influenced on the one hand by the material itself and on the other hand by the proper compaction. Because if it is not properly compacted and not suitable or less suitable material fill is used, then we can expect settlements, self-settlements, yeah? Not the settlements of the ground of up to 3%. It means for a 100-meter high embankment, up to 3 meters. And it's really quite a lot. And on the other hand, if the material is suitable and the compaction is properly done, then we can reduce this number by 10 times to 1 to 3 per mil. Yeah? That means up to 10 centimeters to 30 centimeters for a 100-meter high embankment. So there is a real sense and there is a real purpose for focusing on compaction and definitely on compaction control. And what we can see here, some images of the Liesertal embankment. This is the area of the 100-meter high embankment. And maybe you can make out this little spot here. I've marked in yellow. It is nothing else than the roller which was responsible to do all the compaction of this 100-meter high embankment. Yeah? So it's a really very, very small thing. Yeah? And this is an old roller, this is a modern roller. And this time, you see, it was in the end of the 70s. The technology was right in the beginning, but nevertheless, it could be done that the self-settlements were in the range of about 8 to 15 per mil, which is not too much, taking into account that the whole embankment was made of clay, silts, and silty sands. Yeah? So it is, I would say, less suitable material, but finally it worked. And as already mentioned, it was in October 1992 when Professor Brandl invited me to form this group for soil dynamic research. And within the 30 years, we did a lot of projects I've listed here. I do not go into detail, and it is not possible to talk about all of them. So I have chosen some out of them. Definitely, I will talk a little bit about the dynamic load plate test as a spot test. But the main part of my presentation will cover the dynamic roller compaction and continuous compaction control, as everybody can expect. And I have seen also here in the poster, thanks for designing that in the nice way, that you obviously have expectations with respect to this topic. Then if there is time, some words about the deep fiber compaction and new developments. It was also a wish of Igor to talk about that. And finally, a recent research, compaction and railway engineering, and here in particular about condition-based damping process. But before we start with all these developments, about all these invitations, I would like to give an overview about the fundamentals of soil compaction as a kind of a warm-up. So most of you will be familiar with that I talk about, but I think it is necessary to be aware what it means to compact, because we always have to deal with a very special material, and this very special material is soil. On the one hand, we can classify soil according to the grain size, as we all know. So we have the coarse-grained part, we have the fine-grained part, but moreover, we have to take into account the surface roughness, we have to take into account the grain shape, which is well known because it is visible for the eye for the coarse-grained material, but it is not so obvious how it behaves, how it looks like for the fine-grained cohesive soil. And taking into account the mineral content, we also have to have a look to the consistency, to plasticity, all these properties which influence the behavior of this soil significantly. And moreover, the influence of the water, the permeability, is also a very important aspect which always has to take into account. But it is not only the grain size, it's also the grain size distribution which has to be taken into account. And if you have a look to some typical grain size distributions, for instance here, mainly gravels, uniformly grained, intermittent graded, or well graded, they are all very suitable materials for embankment construction, dam construction, for earthworks in general. So they can be well compacted. And if you have a look to sands, yesterday we had an interesting talk about that. Sands are problematic soils to compact. Yeah? So some other aspects have to be taken into account. The mineral content again. So we always should try to have a kind of cementation, but it depends if it is calcareous or not, for instance. Or if possible, we should try to have a very specific water content to gain a kind of apparent cohesion. But nevertheless, sand compaction is a very difficult task. Widely grained grain size distribution are well suitable, and we also have to focus on the fine-grained soil, which are usually problematic soils to be compacted, and sometimes it is necessary to stabilize them with lime, cement, etc., etc. But we always have to handle with all these kind of materials because we just have to use the materials which are available. Yeah? And if they're, for instance, only clay silts, then we have to deal with them. Yeah? And that is the reason why I have to focus on all of them. But it is not grain size distribution alone. Moreover, we have to take into account that soil is a three-phase system, to say it in simplified words. And we all know this phase diagram, which is shown here on this slide. And besides the soil particles, we have here our void, and the voids are partly or fully filled with water. Just in the dry condition, there is only air in the voids. Yeah? And once again, if you have a look now to the structure here of the soil, here the both graphs below, fine-grained soil with a closed void space, but nevertheless with a quite large void space, and for instance a coarse-grained soil with an open void space, but with a relatively small void rate. And we can define a lot of numbers. For instance, the degree of saturation is presented here, or as presented here, the pore void ratio. And taking into consideration these factors, we can have a look to one of the most important relationships with respect to compaction. It is the dry density depending on the water content. And this can be graphically shown here. Every one of us knows that dry density over water content. We can see here the degree of saturation of 100%. It means fully saturated soil. And then the blue isolines for different numbers of the degree of saturation. But of interest in soil mechanics is just a very small part. It's about this. And if you have a look into detail of that, then we can see with exactly this, we can now get an in-view into the compactability of the soil, into the compactability procedure, which is usually done in laboratory with the Proctor test. So we all know this test. So the standard Proctor test here yields, for instance, this Proctor curve. That means there is optimum water content where we gain the maximum dry density if we apply more energy as presented here in the modified Proctor test. We see what we expect, that the dry density is higher, but the maximum water content is lower. And the explanation is quite simple for that, because the void volume is much smaller and there's not so much space for water there. Yeah? And what we can see once again, here the line of saturation, full saturation, and here the line for a saturation degree of 70%. The maximum density, dry density, is always in between here. So what do we get out of this test? Proctor density, optimum water content both for standard and modified Proctor test. And when we compare it now to the dry density, which we gain in situ, we can define the degree of compaction as presented here. We'll go into that a little bit later because this is an important relationship. And this Proctor curve is a real property of each soil. And for each soil, you will gain a different curve. And on the left-hand side, we can see typical Proctor curves for gravel and sand. And what we can make out, for instance, for sands, they're very flat, they're very shallow. That means there is not a big compaction potential. And we can also see that the dry density, which can be achieved, is quite low. And if we have a look to the right-hand side, to the silty clays, in general, the level of the dry density is lower. There is one main reason for that. It is the closed void space, so it is more energy needed to gain a higher compaction, but the energy applied is defined by the Proctor test, and so the maximum density, maximum dry density we can achieve is definitely lower. And if you have a look now to the general properties of soil, to the typical soil characteristics, we can make out that gravel and sand on the one hand, that means the coarse-grained soil, and the silts and clays, the fine-grained soils, are behaving totally different. Yeah? I do not want to go into detail of that because I think that you will get all the slides afterwards to have a view on that. But I would just focus on the compaction, because if you have to take into account how compact gravel and sand on the one hand and silt and clay on the other hand, we see totally different techniques have to be applied. Yeah? So for coarse-grained soil, what shall be done? A virtual elimination of internal friction. That means a rearrangement of particles into denser fit, as we can see here, for instance. Yeah? So vibrations are most effective for compacting gravel and sands, and that is the reason why it makes sense to apply vibrations that mean a dynamic load to compact gravel and sands in the best way. On the other hand, if you have a look now to the structure of the silts and clays, then what do we have to do? We have to exceed the cohesion forces. That means we need to squeeze out the water and the air out of the closed voids. And vibrations, dynamic loads, are definitely not the best technique, not the best method to achieve this. The best one is to apply a dead load, a static load, or to open the closed void space by kind of a kneading process. Yeah, and there are many aspects which are influencing now this compaction, but we will definitely talk about dynamic compaction a little bit later on. And before we do this, I would like to talk a bit about the conventional compaction controls. That means the state of the art, but also about the innovation in this field. So we all know that we can directly measure the density. On the one hand, we can perform the Proctor test. Usually we use the standard Proctor test, but then sometimes also the modified one. So we get the Proctor density, and this Proctor density we compare with the density determined in the field, which can be done by replacement methods, sand or water, for instance, or tube sampling for cohesive soils, or the application of the nuclear gauge method. And if we compare then, as already mentioned before, now the dry density from the field with the Proctor density, we get a degree of compaction multiplied by 100%. But we all know that this kind of testing is not really very reliable. Yeah? It is spot testing. Yeah? So I was never happy with that, and I would say a bit better method was to measure stiffness, because what we know, the denser a soil is, the stiffer it reacts. Yeah? So this is one basic principle. That means we can also indirectly measure compaction by stiffness measurement. So we have different possibilities. California bearing ratio, we usually don't use in Austria. Benkelmann beam is an anachronism. It's decades ago that we use it. So we mainly use load plate tests. On the one hand, static ones, on the other hand, dynamic ones, in order to determine the deformation modulus for different loadings. And before we go into detail of that, some words about the comparison of density measurement and stiffness measurement. Here in the top, we see a typical compaction curve from the Proctor test and the requirement of 97% of Proctor density. And here below, we also can draw the so-called transformed compaction curve, which is derived from stiffness measurements. And we can see there is no coincidence in the requirements. So we cannot really say if we have achieved a sufficient compaction, it's also stiff enough, and the other way around. Yeah? That means, okay, if you're outside of this whole area, there is a common rejection. How do we deal with this in yellow marked areas? Here on the left-hand side, we have sufficient stiffness, but no sufficient density. So stiffness measurement pretends, let's say it in that way, sufficient density. And here on the right-hand side, the other way around, there is no sufficient stiffness, but sufficient density. And in this case, density measurements pretends sufficient stiffness, but it is not existing. So what is the conclusion out of it? And this is valid especially for the fine-grained soil, fine-grained cohesive soils. Always both density and stiffness should be verified in all the quality testing processes, in particular, as mentioned, for the fine-grained cohesive soils. Many people in practice are not aware of this, and also in theory they're not aware of this. Yeah? Stiffness and density are not exactly the same. Yeah? They are correlating, but we also have to take into account what is the requirement, what is the definition, what would we gain, stiffness or density. So coming now to the spot tests. Static load plate tests, every one of us knows about it, and I've learned that also in Croatia, this is one of the main equipment to do all the testing in earthworks for road embankments, dams, etc., etc. So the static deformation modulus is defined according to the elasticity theory. So we yield this relatively simple formula. And if you have a look to the diagram here on the left-hand side, so we have the first loading, we have the second loading, we have before the unloading phase, and from all of these phases, we can define here deformation modulus, which are all a bit different. So we see we apply the elastic theory, but it's definitely not elastic. But we do it because it is simple. Sometimes also this compaction rate is applied. To be honest, this is soil mechanical nonsense. I know it is in all the standards, in all over the world. It is not time to talk about this in detail, but if you're interested, we can discuss this later on. We did a lot of research in this, and so we also tried to expel it out of the standards, but it is not possible, even not in Austria. And I remember also Professor Brandl talked about this, and I can imagine that he talked in his first Nonveiller lecture about this as well. And I've learned, I didn't know that before, that his topic was more or less the same than mine. Yeah? So in 2000, when he delivered his first presentation. So what are the benefits of a static load plate test? Of course, it is a robust equipment. It is proven for decades. But there are also a lot of drawbacks, because on the one hand, you need a counterweight, for instance, a roller, whatever, It is a very time-consuming procedure. No vibrations during the test may occur, because then you affect all the equipment here. And what is maybe new for you, there are always systematic errors due to the position of the reference beam. This is the reference beam within the settlement trough and due to the heave of the counterweight. It is just a couple of hundreds of millimeters, but this can influence the results up to 80%. Up and up to about 40% down. So the range is really very wide. I do not talk about this in detail, but we did a lot of research on it, and unfortunately we have only papers in German on that. And we always have to take into account there are errors. These errors are systematic, but how to deal with that to reduce the requirements. This is the only chance, and this is done. So all the requirements are always on the safe side, on the very safe side. So we have to be aware of that. And finally, there's always a so-called human factor, because the procedure, how to perform a static load plate test, is clearly defined, but everyone is doing it in a bit different way. I did a study 25 years ago with my students, and I said everyone is doing now the test on his own according to the regulations on the same spot or in the same area, and we received different results. So this we have to take into account. That is the reason why it makes sense to think about an alternative, and the alternative is the so-called dynamic load plate tests. We gain from that a dynamic deformation modulus, and we can see there's a very simple formula, and the basis of the formula is exactly the same here compared to the static one. We just here assume that here the stress which is applied is constant, and so taking into account this constant stress of 100 kilonewton per square meter and the radius of 150 millimeters yields this simple equation, 22.5 divided by the measured maximum displacement. So also we have here a typical dynamic behavior. We just consider this straight line, and from this straight line, finally we calculate the dynamic deformation modulus. It is a real simplification. Maybe you will think this is nonsense, but I will show you now that it is not nonsense. It makes really sense. So what is the idea of this equipment? It was already developed by later Professor Weingart in the former German Democratic Republic. This was the reason why it was for a very long time unknown, because it was in this, let's say, iron cage of the country of GDR. But from my point of view, it was perfectly tuned. What is it consisting of? Of a loading device with a falling weight, with a load plate including a deflection measurement device. And the most important part is here the spring damper element consisting of 17 pre-stressed steel disc springs. Maybe you have seen some equipment with rubber spring damper element. Forget it. You cannot gain reliable results on that. And that made this really difficult for a couple of years. And so we did a research project on that in order to get an in-view if and why this simplified evaluation is also reliable. And in the next 3 slides, I just want to show you how we do our research in soil dynamics. So we always do large-scale experimental tests compared with calculations. On the one hand, numerical calculations. So on the right-hand side, you see a quite simple finite element calculation, and you can typically see the dynamic behavior because you always can see the time shift here. So for instance, now you see here this stress is already reduced, while here the maximum stress is exceeding. And this just comes from wave propagation, which always has to be taken into account for dynamic calculations. And on the other hand, both on the equipment and also in the soil, we measure acceleration, but also pressure, deformations or displacement. everything's dynamically with very high precision. And the comparison on the left-hand side shows that the calculation and also the experimental really fits very well. And that was the reason why we said, okay, we can even simplify the procedure. We do not need to do numerical testing because we can see in a well-compacted material, we have a kind of an elastic response. And that is the reason why we applied simple models. In this case, a 2 degrees of freedom. On the right-hand side, we can see the equation of motions. I do not go into detail of that. But what I would like to present with this slide here, how to go along with the simplified formula, if it is correct to apply it in this way or not. So what did we do? So we have the free body system here. We take into consideration the upper one. And we have both the soil contact force and also the soil contact pressure and the plate deflection. And we did the calculation, and what we saw, due to a variation, a relatively high variation of the modulus, we saw that the variation of the soil contact force was insignificantly low. So it was more or less constant. And at the same time, there was a significant variation in the plate deflection. Yeah? So a quite easy conclusion out of that. We always have this force, soil contact force of about 7 kilonewton. This is in according with a stress of 100 kPa. That means it is right that no force measurement is required because this number is more or less constant and only deflection measurement is necessary. That means to keep this stress constant is okay. And yeah, from this point of view, the simplified formula can be applied. But this is not the final answer on that. So the next one we took into account was if the simplified evaluation is correct or not. Yeah? Can it be applied or not? Yeah? And what we have here now, this is now the soil contact pressure plate deflection diagram derived from measurements. Yeah? This is not a calculation, this is just a measurement. Yeah? But we applied the soil model again, and we have a look to the free body diagram here beneath, and you see it is now a single degree of freedom system, a very simplified one with a Kelvin-Voigt model. That means a linear elastic spring and a viscose damper, and we feed this simplified model now with the measured acceleration of the plate, which is integrated to get the plate velocity, integrated twice in order to get the plate deflection. Yeah? So we have the plate deflection here, and the soil contact pressure we can calculate simply then here from the equation of motion, which is well known. But what did we now? We just take into account now the elastic part, we separate it. And why do we do that? Because also in the simplified calculation, we just consider a constant stress. That means we compare this equation to each other. That means on the one hand, we have now the so-called deformation modulus K determination with elastic part. We can see here, so this is this part. And what we get out of it is a linear relationship. And we compare it now with the simplified evaluation. Sure, we also have a linear relationship. That means it looks very close to each other, but the point is that there is a deviation here in the inclination. And this is just one spot out of many. And we did it here for a stiffness from very low stiffness to very high stiffness. And what we can get here is a systematic deviation. It is always the same. That means if you compare the measured dynamic deformation modulus with the so-called ideal dynamic deformation modulus, then we have a deviation, and it is systematic. And if we take into account this for the conversion between the dynamic deformation modulus and, for instance, with the static deformation modulus, we can clearly define very simple equations which are graphically presented here. These are the formulas, and these formulas are now part of a standard in Austria, which we established in the year 2008. I have to note on that the conversion of requirements shall be done with it, within contractual provisions for it, but it is not for the conversion of single tests, because it will never work for single tests. Yeah? So you always have to have this general view on that. Yeah? So we also could prove everything works, and that is the reason why we standardized finally the whole dynamic load plate test. And what we can see, a very cleverly tuned system already done in 1977 by Wolfgang Weingart in Eastern Germany, and the very simplified evaluation here. There is only one drawback, maybe here in Croatia, if you would like to apply it, that this equipment needs a calibration once a year. And this calibration can only be done now in Austria and in Germany. Yeah? But I've seen it's not a problem. We do the calibration here in Vienna. We get a lot of load plates from Hungary and other countries, so it should be done. And maybe you install also such a calibration procedure here at the university or wherever. Then I think you have a very good alternative to the static load plate test. I haven't used the static load plate test now for almost 15 years, because from my point of view, it is an anachronism. But if you have nothing better, it is the best one, yeah, to apply. Yeah. But this would be a real progress to apply this dynamic load plate test. You have only advantages. It's a very short procedure. You have no human aspect, etc., etc. But there are even better techniques I would like to talk about now. Now I come to the core part of my presentation, to the dynamic roller compaction, and sure, the roller integrated continuous compaction control. It's always a pleasure for me to talk about it, because it was here the topic of my PhD thesis long time ago. But having a look to history, the concept of vibratory excitation was already established in 1958. So it's on the one hand quite long time ago, on the other hand it's not so long. And precisely 20 years later, the first CCC system for vibratory rollers was developed from the Swedish company Geotehničkog AB. And just 4 years later, this company, a very small company consisting of 7 people, also developed the concept of the oscillatory excitation. And if we talk about history, maybe some personal history on that, to relax a little bit now. Talking a bit about myself and my relationship to Croatia, and especially my relationship with soil mechanics and compaction, because it started exactly here. You can see me as a almost 5 years old guy. It was an Otto Grab, and I remember well as it was yesterday, when I was playing sand every day in the morning. After the flood was over, the sand was wet, and it was not possible to construct such more or less nice sand castles, yeah, because the sand was flowing through the fingers, yeah. Then during the day it was made possible, and I realized as a 5 years old guy, there must be a connection with water, yeah. So it was drying up a little bit, and then we built this, and even we could construct tunnels. It did not collapse, but in the evening, when the sun burned down and it dried out, it collapsed. And I realized it must have something to do with water. It was drying out, yeah? And the interesting thing, it was exactly the same time when Széchenyi and Kést in Hungary did their intensive investigations about the apparent cohesion of sands, yeah? And they found out if there is a degree of saturation of about 80 to 90%, then there is an apparent cohesion consisting if the water content is below or up, the apparent cohesion vanishes. Yeah, it's no more existing. Yeah, and it's really good remembrance. My family, my father, my mother, my older brother, and me, we spent many times our holidays. But I would like to go 3 years before on my second birthday, because I received the present, and you can see I was really happy about it. And this present is still on my desk. It was a toy roller, yeah. And already this time it was vibrating, yeah. And many years later, after I have married my wife, I realized that I've married the right person, because it's just 4 years ago that my wife, and she is the first female roller operator I met, yeah, did all the compaction for the extension of the old house of her, the house of her parents. Yeah, so 4 years ago, and you can see she had really fun with compaction. Yeah, so obviously it was laid into my cradle to behave with soil dynamics or with soil dynamics, and especially with rollers. Yeah. Okay, coming back to some more serious aspects. Which rollers are available nowadays? On the one hand, static rollers, on the other hand, dynamic rollers. So we just talk about the dynamic rollers. Vibratory rollers with one rotating eccentric mass here at the axle. Oscillatory rollers here with two eccentric masses here apart from the axis but rotating in the same direction. Then we have rollers with control of the vertical centrifugal force. What does it mean? That there are two counter-rotating eccentric masses, and the whole excitation unit can be rotated in order to gain exclusively vertical, any inclined, or exclusively horizontal excitation. Yeah? So it is more or less a combination of that of a vibratory roller and of that of a oscillatory roller. And the last step in development was the idea of the so-called feedback-controlled rollers. I will also talk about this briefly. Going a bit more into detail about vibration, vibratory compaction works in the way that the eccentric mass in the drum axis is rotating in form of a circular translatory vibration of the drum. So we gain mainly a vertical loading and a better compaction depth compared to all other systems. We have to take into account that there are 5 different modes of operations. I will talk about on the next slide. But first of all, also have a look to the oscillatory compaction. There are 2 eccentric masses now. They're eccentric but point symmetric to the axis. That means the distance to the axis is the same. They have the same sense of rotation, forming a sinusoidal torque around the drum axis. That means a kind of a shear force is produced. And the main advantage is that there are very low ambient vibrations due to that. There are also some modes of operation. I will not go into detail of that. Yeah? How do we apply vibratory rollers? So more or less for all dynamically compactable soils and materials. That means, as we already learned, for coarse-grained material, Michelin's grained materials, and in some cases also for fine-grained materials. And it is the mainly used roller worldwide. Oscillatory rollers are employed in the vicinity of sensitive structures. That means in the vicinity of bridges or in urban areas in order to reduce the vibrations. And it is a perfect tool to seal surfaces, on the one hand for asphalt, and on the other hand also for mineral base layers. If you have a look now to the modes of operation of a vibratory roller, this was one of the main outcomes of my PhD thesis in the year 1996, already a long time ago. And we found out that there are 5 different modes of operation. So there is continuous contact. What does it mean? This is the soil contact force. There's always contact between the roller and the soil. And if the soil stiffness is increasing, there is a partial uplift. That means there is a take-off, there is an air phase, a very, very short one, within every excitation round. Yeah? And if the soil stiffness is even getting stiffer, then we have the operating mode of double jump. What does double jump mean? That you can see only every second cycle of excitation, there is a repetition of the signal. That means there is a heavy impact and there is a light impact followed by this. Yeah? And in between, we have a quite long air phase. Okay, about rocking motion and chaotic motion, I don't need to talk, so the drum becomes imbalanced. And if you think about application of continuous compaction control, we can see it can be ideally applied here within the operating condition of partial uplift, also within continuous contact, depending on the system. Maybe with double chunk, but definitely not for rocking motion and chaotic motion. And what does continuous compaction control now mean? It is nothing else than the measurement of the motion behavior of the drum at the bearing of the drum with accelerometers receiving such signals, we can see here the acceleration, which is conform to the force. And here, this line, number 1, is the excitation of the drum. Here, the dotted line of the exciter, and the area between, this represents the soil contact force. On the left hand for partial uplift, on the right hand for double jump. And now, if we evaluate exactly these acceleration measurements, we get continuously all over the compacted area such a picture. That means different colors representing different values and stiffnesses. And if you have a look into detail how the systems can be applied, on the left-hand side above, we have the first indicator for vibratory rollers, the so-called compactometer value, which is evaluated in the frequency domain. That means we just compare the double excitation, the amplitude of the double excitation frequency with the amplitude of the excitation frequency, forming the so-called compactometer value, and all the other systems are based in the evaluation in the time domain. So the first of that was the so-called omega value based on the evaluation of the energy transmitted to the soil. That means here the area in between the soil contact force jump displacement area is the energy transferred to the soil. And further developments show now the EVIP value, which is the inclination of the soil contact force displacement relationship during the loading phase. But as you can imagine, this is not the real stiffness because this is the loading response. And it is not the stiffness because the stiffness is anywhere in between, as we have already seen here with our research of the dynamic load plate test. And the Kp value is very similar. It's derived from the soil contact force displacement relationship at the maximum drum deflection. So we have 4 systems, and we really had to check them if they reveal stiffness, compaction, or whatever. And so we did, once again, experiments. On the other hand, also calculations. Here's some finite element calculation showing now the dependencies. What do we have here? On the horizontal axis, we have the Young's modulus. That means the stiffness of the ground. On the vertical axis, we have the vertical amplitude of the excitation, but related to the maximum amplitude from 10% to 100%. And what we can clearly see, there's obviously a dependency on the modes of operation, and there must be also some other influences, because there's only an independency of the roller parameters, for instance, and also of the modes of operation if the isolines would be straight vertical lines, because then we wouldn't have any influence of the roller parameter here in exemplary from the drum amplitude. So what does it mean if you have a look now here, due to this section of about 80% of the maximum amplitude, we get this graph, and what we can see is between this dotted line, we have a clear increase with the Young's modulus, that means with the stiffness of the soil, which works very well for CMV, EVIP, and Kp, not so well for omega. If you have a look here to the left side, then we see, okay, for omega, Kp, and EVIP it works, but not for CMV. And here on the right-hand side, that doesn't look very nicely. And what does it depend on? The modes of operation, yeah? So we have here contact with partial uplift and with double jump. And this is now the answer why CCC always should apply during partial uplift. Then obviously all these 4 indicators give reliable results. Yeah, so we did the research. It is not so long ago, just a couple of years, I think about 7 years ago. We investigated the dependency on all other machine parameters and also operating parameters. For instance, you can see here an artificial weak spot, and all CCC indicators detect this weak spot. So we have here a variation of the roller speed, 2K, 4K, and 6K. And what we can see, in tendency, the values get a bit lower. That means that the soil seems to be softer for higher roller speeds in tendency. And the time domain-based values, omega, evip, and kp, are obviously less sensible compared to the frequency domain-based CMV. We did some more variations, for instance, the frequency and also the amplitude. And what we can see here, having a look to the frequency, CMV and omega decrease, while evip and kp increase. Having a look to the amplitude variation, then we can see that CMV and omega strongly are influenced by the amplitude, and evip and kp are more or less uninfluenced. And this is one of the hurdles in applying the CCC, because we just get relative values and not absolute values, like the static or the dynamic deformation modulus of the load plate test. Yeah? So what to do? There is a simple answer: do a calibration. But this calibration has to be done always for every layer, for not for all layers, for all typical soils. And what we have to take into account are the different depth effects between continuous caption compaction control. This is about 1.5 to 2 meters. And spot tests like static load plate tests and dynamic load plate tests, which is just 50 to 60 centimeters. So there's a real gap in between. We have to take that into account. But nevertheless, we can do it if we know what we do. And what we recommend now in our standard, to select low values, which are here the red areas, to select mean values from the green areas, and to select high values from the blue areas. So we can determine the linear regression line, and if the regression factor is larger than 0.7, then it is okay. And what we are doing now, we are setting limits now. So we start with a reference modulus. For instance, this is 35 meganewton per square meter, just to give you an example. And then we have a procedure defined in our regulations already from 1999 to gain a so-called 80% minimum value, a minimum value, a mean value, and a maximum value. And if we compare it now with a typical result, with a lane plot over 25 meters here, then we can see 4 different roller passes. We can clearly see the increase of them, the first, the second, the third, and the fourth. We can clearly see that the results are reproducible, and we can have a look if they're uniform or not. Here they're obviously not very uniform. That means we have 2 more, two more aspects we can take into account. On the one hand, the increase of the mean value. If it is less than 5%, almost no more compaction is possible with this applied roller. And we also can define the standard deviation. And the big advantage of these 2 aspects is that no calibration is needed for. For all the others, we need a calibration. So having a look, concluding that to all the procedure, what has to be done in the beginning, first of all, measurements, setup of correlation, according to the standard we've already designed, as mentioned in 1999, and then setting of the limits. It is important to define the lanes, the positioning of the roller. Nowadays, it is done GPS-based, so it is quite simple. And now we start. With the first pass, what we can see here, a lot of red spots. That means, obviously, insufficient compaction. So we have a limit check here of all the defined limits. We have a compaction progress check, and we have the uniformity check. Okay, here, obviously, we see no sufficient compaction, second pass. Looks much better, but still some red spots here. Third pass, everything's green. And the limit check says, okay, everything's okay. So you can see the main hurdle is the calibration. The application is quite simple because the tools are developed in a way that you can apply them really in a very simple form. But what to do with the calibration, yeah? We were thinking about in the last 10 years how to expel here calibration, and that is the, yeah, what did we do? We developed a totally novel CCC indicator, and the idea behind was to develop it in a way that is more or less roller independent of machine parameters. So, and just to give you a very simple presentation on that, it's the first time ever that I do it here, because this work was recently finished. The oral examination will take place in about 1 month, so it is really brand new. So, first of all, the mainly vertical loading of the subgrade caused by vibrating drum results in a measured soil response. That means already the well-known force displacement diagram. We have the loading phase, maximum force, unloading phase, the takeoff, that means the air phase, and then the drum comes back, hits the ground, beginning of contact again. In the second step, the measured motion behavior of the drum now gets applied to pure geometric model, taking into account plasticity of the soil. So we take into account the plasticity of the soil. That is new, but I think it is important because compaction is always plastic deformation. Yeah? So it is a very complicated procedure I do not present here. And what you can see here, this is the development of the width of the drum with the penetration depths. And we can see loading, unloading, and the air phase. What do we do with that? We determine the contact geometry between the drum and the subgrade. In the next step, the measured motion behavior, already presented here, of the drum, with the corresponding contact geometry, gets now imposed on a suitable soil model, which is as simple as possible to determine the theoretical system response. You can see a very simple model. Once again, Kelvin Voigt. We have a linear elastic spring, we have a viscose damper, but we have a varying contact geometry. We have the simple models which are derived from the Wolf cone model, and here the result of the simulation model. And what we can see here, they do not really fit together, because we can start with values whatever we want. But what we can develop in the beginning is the unloading stiffness factor. That means a different inclination for loading and unloading. And we have already defined the begin of contact and the loss of contact. Yeah? And in the next step, what do? We match now both models to each other by applying the matching theory. That means matching model to measurement by adjusting now the soil model input parameters. And these are the Young's modulus and the damping factor. And the Young's modulus and the damping factor are always constant values. And you can see, after some steps, we achieve a best fit. This best fit really fits now to the measured soil response. And taking account a little correction, I do not go into detail about the comparison of the measured static load and the simulated static load, we now receive the innovative value, the EGU, and this EGU is nothing else than a corresponding value to the Young's modulus. And now maybe you will say, okay, this is a curve, this is not a straight line. But nevertheless, E is constant. The curvature is just coming from the changing geometry of the drum, from 0 to the maximum value. This is the reason why it is curved. Yeah? But this value is constant. Yeah? And if you have a look to the validation now, on the one hand, the trends, we can see now the comparison with CMV, omega, EVIP, and KB, that all the CCC indicators are similar to each other. That means we also get this reproducible trend. And now, more interesting, the dependency of the roller parameter. And what we did now, a comparison between the forward pass and the backward pass. As you can see, the forward pass, the backward pass. Unfortunately, we cannot see it quite well here. So the backward is the lighter line. And it is, we cannot really make out. I'm really sorry for that. Yeah? And we can see for each EGU, it is largely independent of this parameter, and we could show even of all the other process parameters. That means we really found a fully independent value. And this value is a real potential for the future to the case that we do not need any calibration anymore. And what is the background? Just summarized, EGO describes the Young's modulus of the soil, and thus a physically based soil stiffness characterizing the quantity with corresponding unit. And it is a largely device and process parameter independent CCC indicator. And one more advantage, it is definitely insensitive to the modes of operation. That it means it works for continuous contact as well as for double jump, and we do not have all these hurdles to overcome this transfer zone between continuous contact and double jump itself. Yeah, and just finally, another development, just on one slide, we also developed a novel system for oscillatory rollers, just to give it you in a very brief overview. So we measure once again the accelerations. We did it both in the ground and also at the bearing of the drum, that means here at the axis. And we could see a very characteristic behavior of the soil accelerations, which replicate more or less in the same way in the bearing of the drum, forming this nice H-shape. This is the H-shape of the accelerations in horizontal and vertical direction for the second pass. And we can have a look to the 11th pass. And what we can easily see, if we compare to each other, they're quite similar. But here, the maximum acceleration amplitudes both increase, and thus also the area in between increase. And so we have found a very nice and a very simple indicator for oscillatory rollers. It is just the surface area here within this H-shape of the acceleration of the bearing of the drum. Coming to the end of this topic, I mentioned it briefly, rollers with control of vertical centrifugal force and feedback controlled rollers. What does it mean? We have already seen it before. Now a combination between a vertical and a horizontal, that means between a kind of a vibratory and a kind of an oscillatory drum. And we can use both advantages of those if we just rotate the whole excitation unit. And this is usually done by the roller operator itself. That means if he's experienced one, he exactly knows how to adjust now the exciter unit, depending on the soil type, on the layer thickness, on the effect of vibration to adjacent houses, whatever. But we need experienced roller operators. Yeah? If we do not have them, or even if you would like to optimize the process, we can automatize this. That means we can have an automatic control, but we need to define control criteria. And these are quite simple. I think every one of you knows now what is the main one to prevent double jump. Yeah? That means the main control criteria is exactly this, the prevention of double jump, or we also could define the maximum soil contact force. That means, as we can see here, this was also one test we performed already in 1998 with a small weak area, with a large weak area, that here is an automatic control of the direction of the exciter unit. So we optimize the compaction process, we improve the uniformity, we prevent overcompaction like grain crushing, reloosening, etc. And we take into consideration continuous compaction control. Okay, for the manual adjustment it is possible. But what is the requirement? That the process parameters, the device and the process parameter must be constant. Amplitude, frequency, and velocity. So it is possible to apply the CCC. For feedback control rollers, it is not possible because there is an automatic adjustment exactly here of these parameters, in particular here the amplitude. So it is not possible to apply continuous compaction control for feedback controllers. Maybe in future it is possible for the novel indicator I presented you, because this is independent of that. Yeah? But this is now part of future research. And coming now to two case histories. On the one hand, a project in Austria we performed in 2015. We can see here a road, embankment part, a cut, and embankment part again. Here the cut was done excavation in rock. We see a lot of blue spots. That means very high values. Sure, the stiffness of rock is relatively high. And in embankment area, the higher the embankment gets, the greener it gets. And here on the other hand, so we could reveal a mistake which was done by the company because the company forgot to remove the weathered rock deposits. And that could be clearly seen here. This is a detail of that. And you can see the red spots. You can see it also here. This is exactly the transition zone between the cut and embankment. And what was the solution? Okay, on the one hand to excavate everything, on the other hand to do some additional spot testing. Yeah? And it revealed, okay, it was okay. It was not the optimum, but it was okay. And so we could accept this result. So you can clearly see with just looking here on the result, how is the quality of the road. This is one of the benefits of continuous compaction control. And you exactly know where you have to look in detail. Yeah? And maybe another brief example, it was already in 2004, was the Shibuya concrete face rockfill dam in China. And I took these photos in one of my site visits. It's a huge dam. It was the biggest of this kind. 15 million cubic meters of material had to be filled. The dam height was more than 200 meters. It's really a huge embankment dam. And here you can see little 3 spots. And these 3 spots are the rollers which did all the compaction. And the main challenge was that daily 15,000 to 20,000 cubic meter of material had to be filled and compacted. And this should have been done with 3 rollers. And this was only possible with feedback controlled, direct control rollers, with the very heavy ones with the 25 tons. And the quality assurance was done with other rollers applying continuous compaction control, in this case with a whip, where constant roller parameters were applied. Yeah, summarizing continuous compaction control. Beginning in the year 1978, work and roller integrated online high quality control. We have a continuous control covering all the compacted area, which is not possible for the spot test. We have a decision-making support, first of all for the roller operator, but also for the site inspector. We have a custom quality documentation. It is a standardized procedure in the meanwhile. For instance, these are the standards in Austria. As already mentioned, the CCC guidelines from 1999, then Earthworks guidelines from 2010, now revised last years. And you can see the application of CCC is compulsory in Austria here for these areas of an embankment, and it is highly recommended to apply it to every part of an dam, of an embankment, of all earthworks. The method is economic and time-saving, and it is still innovative, as we have seen with eGeo and the CCC OSCE indicator. What are the present challenges? On the one hand, the calibration of the roller parameter depending on CC indicators. That means CMV, omega, EVIP, Kp work, but they need calibration. And unfortunately, it is not established everywhere in the world. That means in many countries, standards are missing. But nevertheless, there is a kind of a generalized standard which is provided by ISSMGE, which can easily apply to standards in all of the countries. Yeah, and it was just 4 years ago that we celebrated 40 years of roller integrated continuous compaction control. And also 2 of my friends from the Croatian Society, Krunoslav was there, and also Mensur was there. Thanks a lot for coming to Vienna for this event. I think it was a very nice one. And all people still living, all people that were alive at this time were also, who took part in the development of CCC, were taking part in this symposium. Okay, so it is up to you. If it is okay, I will continue with that, deep vibro compaction, because it was also a short discussion with Igor, and he said it should be interesting to talk about that. So at the beginning, I thought it is maybe too much. Yeah? especially talking about the vibratory integrated compaction control. You see one more continuous compaction control system. And you all know the deep vibro-compaction, also named vibroflotation, for a deep compaction of soil, for homogenization of coarse-grained soil. That means we activate the soil compaction potential by penetrating here the dynamically excited vibrator, facilitating a water feed, and while we pull out in the backstep method, that means pull out, penetrate again, we compact the soil to a certain extent here. So what we gain is the so-called compaction funnel we can see here, and we also can see here the water, and this has to be backfilled, and finally we have a quite homogeneously compacted space here up to a depth usually applied 25 meters, but there were also projects in Asia up to 100 meters. Yeah? And this technology was already patented in 1933 to 1934 by the Keller company in Germany. And in 1976, an online control system was developed, the so-called ampere depth recorder. And maybe many of you know that. I was always very skeptical on that. Yeah? Just to measure the power consumption, and power consumption is related to compaction or to stiffness. I was definitely not sure about if it works, but we'll see the outcome of that. Yeah? And then in 2018, that you can see it was always 42 years in between the patent, the development of the ampere depth recorder, and the first CCC system for deep vibro compaction was developed at our institute, and would like to present it briefly now. So how is compaction control done? On the one hand, with indirect methods, dynamic probing heavies or cone penetration test, while cone penetration test is not so suitable in grains and sands, as we all know. So in Austria, for instance, we just use the dynamic probing heavy equipment, but we also can do a documentation of production parameters like the fill material consumption, the penetration depths, the pull down pressure, and the power consumption of the vibrator motor. That means this is the ampere depth recorder I'm very skeptical on. And nowadays we also can visualize with the vibroscanner development of the Keller company. For instance, spatial data, as we can see here, the position and location, the penetration depth and length, as we can see here, fill material consumption, etc., etc. Here in the middle we see the comparison of our dynamic probing, the number of blows, N10 we use in Austria, before and after, and we see the compaction progress. And on the right-hand side, a typical log recording over time, the penetration, the power consumption, and the pull down forth. Okay, for me it was not really satisfying, and we did a lot of projects all over the world, successful one, but always this before and after compaction control, what happens in between, is it sufficient or not? We just know it after, if the work is finished. This is not really satisfying. Yeah? So what do we do? So we can see here on the top the vibrator depth. That means this is the first penetration. Then we can see here the backstep method. Penetrate, pull out, up to the surface. This is the so-called backstep method. What happens, this is our hypothesis. We have a kind of fluidization due to vibration. That means the grain are in a kind of suspension. That is the reason why water feed is so important. Yeah? But it's not liquefaction, yeah? Because there is no pore water pressure. This is one of the requirements for liquefaction. So it's fluidization. It's a difference. Yeah? Then we have compaction due to vibration and penetration. So a grain rearrangement occurs, and okay, that we do step by step up to the top. And this was one of the real interesting results. We always thought that this vibrator is vibrating around the hinge here. No, he's vibrating like a rotational hyperboloid. Yeah, it is not a straight line. Yeah, it is this very interesting shape. And we measured it from accelerometers here on the tip and here near the hinge. And we also measured the pulse with a pulse emitter, the phase angle. So we can see the result here in the middle of the accelerometer in the tip, and we can see the phase angle here down here. What we already can see here, the phase angle is about 90 degrees. And what does it mean if the phase angle is 90 degrees? Resonance. So resonance always has to be taken into account. But I let you know, even now, it is not so important as we always thought before. Yeah? Resonance is definitely not the leading factor for compaction, for deep compaction. Yeah? So if you have a look now to 5 back step periods, we can see on the one hand periodicity, both for the amplitude and for the phase angle, and we can also see the reproducibility, yeah, from backstep to backstep. Yes, and if you have a look now to one backstep in detail, what can we see here? We can see 4 phases. Blue one is the lifting. Then we have now the pull down phase, and we see a slight increase of the amplitude, and we see a clear decrease of the phase angle. Then we reach the point of resonance. Then we have the so-called post-resonance phase. And then usually the operator of the device says it's enough. But what we did, we pushed down. Yeah? It was almost not possible anymore. There was such a resistance of the soil, but we did it. Yeah? And what did we get? An overload. And what can we see here? Here, a peak from our pull-down pressure. Yeah? So this was not really sound for the equipment, but nevertheless we did. And then we relieved everything and lifting again. And what could we see from that? This is exactly the same progress compared to eccentrically excited single degree of freedom system. That means we can see it here. It means we have a rotating excenter. We have some additional soil mass. And once again, we have our Kelvin-Voigt elements. That means a stiffness, elastic stiffness, and we have here a viscose damping factor. And if we take into account now here the frequency ratio is now the damped eigenfrequency compared to the undamped eigenfrequency. And this is always going conform with the increasing of the spring stiffness. So we can conclude from that, okay, when it happens here with a simplified model, it also should happen here, increasing soil stiffness. So we formed a very simple model again. You see a single degree of freedom system in 2 directions, but the same formula. And now taking into account the measured amplitude and the measured phase angle, we get the stiffness. We called it the state-dependent stiffness indicator. And how is the progress now? You can see here it on the left-hand side. There is a point where there is a sudden crease. Yeah? So here it's obviously quite soft, but here it gets stiff. And what is the working hypothesis behind this? If we take a look into the grain skeleton. So we start with a compaction. And what does compaction mean? Contractant behavior of the soil. That means reduction of the pore volume, rearrangement of the grains. We have lateral compression and displacement, and the increasing number of grain-to-grain contacts. And then we have a point. We do not have any reduction of voids anymore. Maybe we also get a kind of grain interlocking. It is only temporarily. And a clear influence on the soil stiffness. That means a kind of dilatant behavior. Yeah? That means a volume increase of the soil. Yeah? Because it's so heavily compacted, it is no compaction possible anymore. And there is a clear point in between we can see here. This is exactly the state-dependent stiffness indicator. So if we have a look at the soil behavior, we have contractant behavior until this point, and then dilatant behavior. And now it is important, does it happen just here for one backstep? Is it comparable to all the other backsteps? And the answer is quite simple. Yes, it is comparable, and we can see it always happens in the same range. So we have a clear transition zone between contraction and dilation. And if we compare now these results to that of the power consumption of the vibrator motor. This is the graph here. We have a clear linear relationship in between. Yeah? So my skepsis was wrong, and it really works. And it works in a way I was really astonished about. It is a clear linear relationship in between. Yeah? Okay, here up to the transition zone, that means maximum stiffness. And then we have the post-resonance and the overload. Okay, this is of clear physical background why there is no correlation. I think I will not go into detail of that, but this is taken into account resonance of a system clear that we have no clear correlation here. But it's not, I think it's not necessary to talk about this because usually compaction is clearly finished at this point. And the experienced operator knows exactly when he stops. And we did nice tests with experienced and unexperienced ones. And the experienced ones, they had a button to push on when they think they have gained full compaction. And it was always exactly this point. And the unexperienced did it always here in this range. Yeah? Because, okay, we have to push down. There is more compaction possible, but it was definitely not. Yeah? So the power consumption of the vibrator motor, so the steps recorder is okay. Yeah? So skepsis was wrong. Yeah? And the comparison to the dynamic probing, dph, we can see here the penetration phase of the vibrator. That means no compaction, it's just the penetration with vibration. So more or less we measure the virgin soil conditions. And it was amazing for me again, if we take into account the different size of the vibrator cone and the dph cone, it is more or less conform. So already during penetrating the vibrator without compaction, you have an online control system now. Yeah? We have patented this 4 years ago, and Keller company is just working on implementing it on all vibrators. So in the future, we also have here a continuous compaction control system for deep vibro compaction. Coming to the last topic now, condition-based track damping, ballast compaction. And it's a pleasure for me to let you know this is the last Croatian contribution of our institute, yeah? Because Olja Babja, she came with me from Vienna. She finished her PhD thesis exactly 13 days ago with an excellent oral examination in Vienna. And on the one hand, I would like to thank Professor Avanas, Željko Avanas. I don't know if he's here now, because last week I think he was in Korea, was, I would say, one of the basic mentor of Olja, because she studied in Rijeka, and sure, also Professor Vriklian, Ivan, was one of the mentors. I would say both of you are responsible that finally Olja remained in geotechnical engineering, came to Vienna, did her diploma thesis at BOKU, that means, you know, the other institute at the University of Natural Science, and then changed to my institute and did an excellent work on that. And on the other hand, the second reviewer, so Željko was then the first reviewer, and Janko was the second reviewer from Ljubljana. He wanted to come, unfortunately, he didn't do it, and he could not be with us 2 weeks ago because he had a bad injury in mid of July. But for me, again, a circle closes, because it was also Professor Šukle from Ljubljana who was the mentor of Professor Nonveiller when he finished his PhD thesis in the year 1957. And the topic, and thanks to you, Sonja, for all the information, was on non-homogeneous embankments, the stability investigations. Yeah? So also a closer topic to that. Yeah? And due to the fact that Olja is here today, and she can do it much better than me, I would like to ask you to give a short presentation within the next 5-6 minutes about your PhD thesis. This is the Croatian contribution which was performed in Vienna in the last 7 years.
I will try to compress the last 6 years in 5 slides. That shouldn't be a problem. No? The topic of my doctoral thesis and also of the research project behind was the development of condition-based track tamping. And since this is a topic that's quite new to most of the people, I would just like to start with answering a few whys and hows. So why do we conduct track tamping? How do we conduct it? And what was, let's say, a motivation or a problem statement behind my thesis? Over the years, or independent on the traffic loads, usually a certain level of deterioration of track geometry occurs. And those geometrical problems are usually irregular in nature. That means that they decrease the safety of travel and they increase the dynamic loads. And in addition to these geometrical problems, also due to traffic loads, the properties of ballast material changes. And this process is called ballast fouling. So if we have a look at this new clean ballast matrix, here we have only skeletal grains and we have voids that are filled only with water. And as this process of ballast fouling progresses, we see that the voids are filled with distance grains and also with filler grains. And not only that, but the change of the particle changes, the shape of the particle changes, and of course with that the characteristics of the track ballast change. The next question to answer would be, how is track tamping conducted? And the answer would be by using the so-called track tamping machines. One of them you can see here on the slide. This is the Plaza Untora 4X tamping machine. The 4X stands for it being able to tamp 4 sleepers at once all together. The tamping machine itself consists of two separate parts. The first one is the lifting, leveling, and tamping unit, and the second one is the DTS, the dynamic track stabilizer. I'll just concentrate on the first part of the process today. So it works approximately like this. The track is lifted obviously by the lifting unit, and it's positioned in its correct geometrical level. At the same time, it's aligned. When doing this, there's a void that's created under the sleeper, and into this void, the ballast material is filled and compacted. The tamping process itself, so process on one sleeper, can consist of between 1 and 3 squeezing processes, including the tamping unit relocation to the next sleeper or to the next group of sleepers. The squeezing process consists of 3 phases. So first of all, the ballast penetration, the tamping unit, including the tamping tines, which are these parts here, are lowered into the ballast. The tamping tines penetrate the ballast, and this process is then followed by the squeezing movement. Squeezing movement is the most important part of the process. This is the part of the process where ballast compaction takes place. And it actually consists of 2 different kinds of movements. So we have the absolute one. This is the closing movement of the tamping tines towards the sleeper, and at the same time they oscillate with a frequency of 35 Hertz and an amplitude of between 4 and 5 millimeters. Last but not least, in the last step, the tamping tines are opened and pulled out of the ballast simultaneously. The idea behind this project was actually to try to make a step forward in the direction of automatization of the whole process. And in order to do that, of course, we try to record the process of track tamping in situ. In order to do that, we developed a measurement system. And here you can see the tamping unit of the before mentioned 4X tamping machine. We applied some sensors to the unit, so we used the string gauges to measure the force on the contact between the tamping tine and the track ballast. We used the laser rangefinders to measure the squeezing movement of the tamping tines, accelerometers to measure the oscillation of the tine, and also we measured the pressures in the cylinders. To make a long story short, what was the point of this measurement system? To look as much into detail as possible and to analyze the dynamic of this process. So the results were presented in form of before mentioned low displacement curves. So one low displacement curves actually presents one single cycle, one single tamping time oscillation backwards and forwards. And with a frequency of 35 Hertz, it has an approximate duration of 28 milliseconds. We use this system to analyze approximately 10,000 sleepers in different locations in Austria over the last 5-6 years. A low displacement curve has the oscillation displacement on the x-axis and the contact force on the y-axis. And in addition to those two characteristics, we also use the area within the curve to calculate the energy that's transferred between the tamping time and the ballast. Also the inclination in this loading and unloading phase that Professor Adam mentioned before, this loading and unloading response that's somewhat similar to the stiffness, but not exactly the same. And also we were able to determine the exact position of the start of contact and end of contact between the tamping time and the ballast. So in the next step, and an effort was made to also develop a mechanical model that should be able to simulate ballast behavior that we have observed and measured in situ. In a shortest possible presentation, this mechanical model is actually a presentation of the interaction between the tamping time and the ballast matrix. It consists of two parts. Here we have the tamping unit. It's dependent on the geometry of the tamping machine. And on the right-hand side, we have the ballast matrix. This was maybe the more tricky part to model. The model is able to simulate both elastic and plastic deformation of track ballast doing compaction. And maybe also more importantly, it's able to model ballast behavior in different phases of ballast falling. Why is this that important? Presented down here, you can see some low displacement diagrams. The ones plotted in red are the ones from the in situ measurement. So going from the left side to the right one, we have low displacement diagrams in clean ballast, in moderately clean ballast, and in foul ballast. So we can see that there are some really nice significant differences between different stages of ballast falling. What we can see, the maximum reaction force per cycle increases with the progress of ballast falling, and we can say a similar thing for this loading response and also for the energy that's needed for compaction. The next question to answer maybe would be, okay, we measure this in situ, but why does this happen? We have observed, especially when compacting clean ballast condition, this phenomena that Professor Adam also mentioned before of ballast fluidization. So in this case, it doesn't have anything to do with water, but still under these dynamic loads, we have observed that especially in clean ballast conditions, we have this severe but temporarily reduction of ballast stiffness and also of the ballast shear strength. So in the next step, of course, we try to do the same thing with the mechanical model. By reducing the stiffness, we tried to also get similar results for all three phases of ballast falling. So the black low displacement diagrams are the ones from the mechanical model, and we were able to use the model and simulate this, let's say, phenomena of ballast fluidization by simply reducing the stiffness of the ballast. In conclusion, I would say the most important results from the project would be that now the tamping machine itself can be used to determine the ballast condition in situ, which then eliminates a need for additional machine employment. We were able also for the first time to really prove that there's a periodic loss of contact during compaction between the tamping time and the ballast, and we were able to observe and measure the triggered process of ballast fluidization. As for the mechanical model, it can be used to simulate different ballast conditions, the ones that we have measured in situ, but also the ones that we didn't encounter. And probably the most important step is that we can now use this mechanical model to test other parameter combinations. So we can test different frequencies, we can test different amplitudes, and hope that we achieve the optimum compaction. In general, the state-of-the-art tamping machines operate with a long list of tamping parameters that can be selected on the site by the machine operator, which then means that we have quite a high human factor, which is okay for the machine operators who have a lot of experience, as you also mentioned before, but it's quite a challenge for new machine operators. So, as I mentioned before, by teaching the machine to detect this ballast condition in situ, we can go towards this automatization of the process, which would then relieve our machine operators and at the same time increase the quality of conducted work. And this is the reason why we have developed this condition-based tamping process.
Olja, thank you very much. For this brief presentation, you did an excellent job as usual. Odlična prezentacija, hvala lepa. Hvala lijepo, sorry, it's not Slovenian. Was really great work, and now maybe you got the impression she was on the leash, but definitely not. It is just a kind of support, especially my young colleagues gave to Olja during all the time, also in difficult times. And once again, thank you to the Croatian Geotechnical Society for Olja, because she did an amazing job, and I'm really happy, Olja, that you were at the Institute for 6 years, and you will always be a part of our Institute, as you know. Okay, ladies and gentlemen, coming to my final remarks now. So fortunately, we're coming to an end now of the presentation of the 18th Nonveiller Lecture. Citing Terzaghi, already in 1925, when he published his first book on Erdbaumechanik, it was called Earthworks Mechanics at the time, he said soil mechanics promises to become a fairly comprehensive scientific subject. It was definitely true, as we see, and with respect to dynamics, in 1948, he wrote in his book Soil Mechanics and Engineering Practice, the effect of vibration on soils may be harmful or beneficial, but it always deserves attention. And it was at a time where vibrations were not part of soil mechanics, because there were more or less no vibrating machines, etc. So he already realized in 1948 the meaning of vibrations of soil dynamics. And what we try to live at our institute in Vienna is still to follow Terzaghi's spirit, doing some totally different work, but I think the spirit is important. And his spirit was always theoretically profound and at the same time practically oriented. Yeah? And this is, from my point of view, the way how to behave in soil mechanics and foundation engineering, in ground engineering. Yeah? And it was in 1929, 1930, when Erwin Nonveiller was student of Terzaghi. And I can imagine, and I talked to Professor Brandl a lot about him, and Professor Brandl knew him from 1964 to 1999, over a period of more than 30 years. And Professor Brandl always said he was a real inspiring person. So we can see, obviously, Erwin Nonveiller was inspired by Terzaghi, and he inspired so many others. And I would say, especially after reading the book which was written by Professor Savic Nosan and by my good friend Ivan Vriklian, yeah, I couldn't stop reading yesterday in the night, to be honest. I was convinced finally that he's one of the giants in geotechnical engineering and a fascinating person. And I can imagine then, later on, as a teacher and as an engineer, as the book is called Učitelje I Engineer, that he inspired so many people here in Croatia and also abroad. He was internationally so active. Yeah? He spoke so many languages, and I think his heritage will be never forgotten. And I always remember a saying that always one of the greatest things is if students and teachers learn from each other. And I think he's a best example for that. And coming to my last slide, I definitely would like to thank all my so-called vibrant team, which was working in the last years with me in the field of soil dynamics. It was definitely not possible to show every one of the last 30 years. These are just the colleagues from the last 7 years, which were working with me in this field. In the first row, 6 out of more than 25 master students who did the master thesis in the field. In the second row, all my PhD students who have already finished or just doing the work in the field. And finally, my so-called leading team, which are supporting me so much for many years or already for decades. And I also would like to thank you, to thank my brother, my older brother. You have seen it as a little boy. He's professor of mechanical engineering at the civil engineering department of the University of Innsbruck, together with his young colleague who was part of my consultancy for almost 10 years and also research and teaching assistant at my institute. They always give me such an inspiration, especially with the theoretical background, the theoretical approach. And so we can see again, there is an inspiration from both sides, from the teacher to the student, from the student to the teacher. And we need the young people, and I always would like to motivate to study civil engineering, to motivate young people to study civil engineering, because it's such an interesting field, and it's just a little spot I presented today, and it is so broad, it is so wide, and I'm really grateful that I may be a part of geotechnical engineering. But it's not only science and academia, it is also the partnership with industry, and these are only 8 of the most important partners. Here beneath you see Heinz Thurner and Åke Sandström. They were the founder of geodynamic and the inventor of the first CCC system. Uwe Blanke invented the terameter, and Roland Anderegg the KB value. And with respect to the current developments, we collaborated with Werner Völkel. Unfortunately, he passed away last year. And with the research in the field of deep vibro compaction with Clemens Kummerer. And here you see now the current 2 bosses of Olja, our collaboration, our excellent collaboration with Plasser and Teurer with respect to all the geotechnical track engineering research. And moreover, and last but not least, I would like to thank all of you. I would like to thank for all the friendship of the Croatian Geotechnical Society, which obviously started more than 110 years ago, I think exactly 113 years ago with Terzagi in Croatia. And once again, Ivan, it was an excellent presentation 3 years ago. And the long collaboration from Professor Heinz Brandl and with so many colleagues here, also the friendship between him and Professor Nonveiller. And yes, it started, or my friendship with the Croatian Geotechnical Society started in 1998. It was one of my first conferences, taking part in the Danube European Conference in Porridge. And my last visit was the Geotechnical Conference in Omish 3 years ago. And these are just some images of some of my friends, and I'm very grateful to all of you. Thank you very much for the friendship, and that's what Igor Sokolic always said, we should keep this friendship. So from my point of view, it will ever last. Thank you very much for your attention. Hvala lijepo, za pažnju.